Let's do the same thing, but with the magnet moving away. You're looking at the cross-section of the coil. So we know there's going to be a change in magnetic flux. Let's calculate in which direction is the change in flux, right? Since let's say that at some initial time the flux was going, as we know, it's going through the magnetic field is going through the loop like that. So the initial flux is pointing that way. If the magnet goes away, what happens to the length of that vector? The final flux is pointing still to the right, but it's smaller. So this is the final flux vector. So the initial is that big, the final flux is that big. So in what direction points the change in flux? It points that way. This is the initial, this is the final. Remember that the initial vector plus the change vector should be equal to the final vector. This vector plus that vector, you put tail with head, gives you this vector. Okay? So this is the change in flux vector, and it's pointing to the left. So the change in flux points that way. If the change in flux points that way, I know that the induced magnetic field is going to have to point to the right. So the induced magnetic field points that way. If the induced magnetic field points to the right, what do I know about the current on the top wire, for example? Right-hand rule. The B, your fingers inside the coil must be pointing to the right. Your fingers inside the coil, in the middle of the coil, must be pointing to the right, because that's the direction of B induced. You end up with a thumb on the top wire pointing out of the page. So that gives you current on the top coming out of the page. If you do the same thing for the bottom wire, you'll end up with a current going into the page, of course, because the current is flowing around the coil. So on one side of the coil it goes up, in the other side of the coil it goes down. Right? So that's how you will use Lenz's law to determine the direction of the current. Right? Let's do another example here. Say that the magnetic field is pointing into the page, and you put a coil here like this. And we're going to look at different cases. A is B increasing. Let's start with that one. If B is increasing, in what direction does the current flow in that coil? So B is going into the page, right? So the flux is going into the loop, right? But B is increasing. So that tells you that the change in flux points in the same direction. It's going into the page, right? The flux is getting bigger. The flux vector is getting bigger. So delta phi points into the page also, if B increases. If delta phi as a vector points into, what do I know about the B induced? It will point out of the page, right? So this is your B induced in here. It's out of the page. So the arrow is pointing towards you. B induced. If B induced points out of the page, the current in that coil goes clockwise or counterclockwise? Counterclockwise, that's right. It should go this way. Put your right hand with the thumb in the middle of the loop, pointing out. Your fingers will curl counterclockwise. So that is your current. The answer here is that the induced current, this is the induced current, is going this way. All right? What if B was decreasing? All right, so in that case, say that B is decreasing. B decreasing. Then what is that change? To begin with, delta phi would be pointing not into the page, but out of the page. If you think of a big vector pointing down, and a moment later the vector is not as big, the difference between those two vectors points out of the page, right? So that tells you that the induced magnetic field is going to have to point in the opposite direction. And if the magnetic field inside the coil points that way, the current is going to have to flow clockwise.